Alrighty, everybody. Welcome to lecture 16. It is officially, I believe, is it the fifth or sixth week? I've lost count of OCSP. I'm super excited to see you all, and let's go ahead and get started. So today we're going to learn about some reactions with alcohols. We're going to talk about how we can convert alcohols into good leaving groups and talk about tosylation and mesylation, which is, again, just a way to make alcohols into a better leaving group. So in Chem 3570, alcohols aren't considered good leaving groups. And would somebody be willing to unmute or type in the chat and talk about maybe why they think alcohols would not be so great to leave in like any of the four main reactions we've covered so far?
Because they're strong bases.
Excellent, Emma. Perfect. They're strong bases, as Emma said, and so they're not going to be very stable with a negative charge. So you wouldn't want to just kick them off of a compound. And yeah, OH is not stable. So as I discussed a slide ago, we're going to talk about how we can convert alcohol into a better leaving group so that we could get rid of it in a reaction. And the first method is protonating the alcohol and then getting it to leave as H2O, because H2O is uncharged and a lot more stable than OH minus. And then we've got tosylation and mesylation again, which we're going to talk about a little bit later. So the first example where we can protonate alcohol and get it to leave is in an SN2 reaction with an alcohol and HX. And remember, X just means a halogen, so HX could be any H halogen like HCl, HBr, anything like that. So in this reaction, I'm going to use HBr. We're going to have that right here. And then we can protonate our alcohol by having a lone pair on the alcohol attack a hydrogen. This creates Br minus. Here we have our oxygen now with the extra hydrogen and a positive charge. And our Br minus is a pretty decent nucleophile. So it can come and do a backside attack and kick off our water molecule. And this is our product. We've now got our alkyl with a bromine on it instead of the alcohol. And of course, we have water as an additional product. So it might seem simple, but this protonation trick is super helpful for synthesis problems where you might need to get rid of your alcohol to get to your final product. A second reaction using the protonization of an alcohol that comes up often in 3570 is doing an E1 reaction with your alcohol and H2SO4. So again, it's got the same idea as the reaction we just covered a slide ago, where we protonate the alcohol first. So I'm going to go ahead and draw my H2SO4, which, if you haven't figured out by now, it looks quite a bit different in organic chem than it does in gen chem. So again, my lone pair on the alcohol is going to go ahead and snag that hydrogen on the H2SO4. So now we have our O with two different hydrogens. And I know last time we showed the the good leaving group being kicked off in a backside attack. However, this is actually such a great leaving group that a lot of the time, it can just leave right on its own. And we've got our carbocation intermediate and our water molecule that's just been kicked off. So what can happen next is that our HSO4 minus, which is the conjugate base of H2SO4, that can act, it's a pretty weak base. So it can come and snag this hydrogen and complete our reaction. And there we go. Are there any questions about this E1 reaction or the previous SN2 reaction that we just covered? Alrighty, I'm gonna move ahead. So now we have a practice synthesis problem, and this is an example of something you might expect to see on maybe a 3570 exam this fall, where we have our final product right here, and we have our starting material. And now that we are armed with a couple of new techniques that, well, I guess just, yeah, it's still a couple two new techniques, it's two different reactions that we just covered, we now have the tools to kind of go about solving this. So I know you all have seen synthesis problems before, but I'm going to go ahead and show one way that you could look at this synthesis problem, which is called, I believe, retrosynthetic analysis. And if you don't know, basically you look at your final product and you kind of work your way backwards to try and get back to the starting material and see what could have happened. So we see on our final material that we have this CN minus, well, not a CN minus, it's a CN attached to our cyclohexane. Does anyone remember what type of reactions CN minus can participate in? Yep, thank you, Arifa. CN minus is a very, very strong nucleophile and base, but we see here that it's attached to our starting material in what is likely a substitution reaction. So I'm gonna go ahead and try and draw, yeah, that's a decent looking cyclohexane. I'm going to draw maybe what could have happened to create this molecule here, our final product. Maybe we have some sort of SN2 reaction where we have X just stands for any good leaving group. Maybe this alkyl reacted with NaCN or HCN or anything like that to create this final product. Well, I'll make that a little bit less confusing. Alrighty, are there any questions about how we came up with this particular step here? Fantastic. Well, let's look at things a little bit further. We see that we have this good leaving group, and we know that we somehow have to get back from this point to this point. So does anyone have an idea or remember from the two reactions that we just covered how we might be able to possibly convert our alcohol into literally any good leaving group?
You protonate the alcohol?
Yep, thank you, Alex. So as Alex just mentioned, we just covered 2 reactions and with protonating alcohols, and one of them was SN2. So perhaps what we could have going on is we could have our alcohol reacting with HX. And again, where X is just any halogen, and that will leave us with this. So that's kind of how a lot of people like to approach synthesis problems, where you can work step by step. And now we see that we have a clear pattern to get from our starting material to our ending material. Are there any questions about this? Alrighty, let's keep moving on. So now that we've talked about our first type of getting rid of alcohol reactions, we can talk about 2 different groups called tosylates and methylates that are involved in tosylation and mesylation. So over here we have tosylate. It's important that you're able to draw out the full group for tosylate with the the benzene in the middle and the methyl, and yes, they are types of sulfate ions. They're often abbreviated as OTS, so make sure you recognize that as well. And as you can see, this is an incredibly good leaving group. So we have our minus charge on one of the oxygens, and as you can imagine, we have a lot of resonance that would go on in this molecule that will be able to keep things very, very stable. And then over on the right, we have our mesylate, same sort of idea. It's got that sulfur in the middle, and the difference is the benzene is no longer present. We just have the methyl here. And once again, we have a decent amount of resonance. So these 2 groups are very good leaving groups. And as you might imagine, one way that we can get our alcohols to leave our molecules is converting them into either tosylates or mesylates. And at this point, I'm going to go ahead and pass the baton over to Samantha.
Thank you. Can everyone hear me? Let me see. Please let me share. There we go.
Yes.
Thank you. I was like, either everyone can hear me and they're not saying anything, or nobody can hear me and then I'm just going to talk to myself. So one or the other. Let me get rid of that real quick. Anyone who can't see my screen right now? Okay, so like Sydney said, generally when we tosylate something or mesylate something, the point of that is to make alcohol a good leaving group. So make OH into a good LG. And so generally when you see tosyl or mesyl compounds, they're going to be tosyl chloride or mesyl chloride, abbreviated as TSCl or MSCl. I was trying to look through literature to see if there were other halides that are used, but it looks like it's generally going to be chloride. I was also trying to think if in 3570 or 3580 you see anything different from this, but I'm pretty sure it's going to be the TSCl and the MSCl. Some of the TAs can correct me if I'm wrong, but you're going to see that they look like basically what we just showed you before. So you're going to have this entire structure, so just instead of that ion, you have that chloride there, and then for the other guy as well, you're going to have that chloride there. And so I'm going to show you how to tosylate and mesylate alcohols right now. They're pretty similar, so I'm going to be drawing essentially the same mechanism twice, so if you only want to draw it once, that is totally fine. And I'm actually going to abbreviate tosyl chloride as this. This is something that you're going to see online a lot of the times. You might also see in class just because I'm lazy and I don't want to draw out that whole benzene ring. So just know that this R group is generally going to refer to this benzene ring plus the methyl. And so if I want to go ahead and tosylate this, I'm going to draw this out. And so remember, you have these lone pairs on the oxygen. They're going to come and attack your sulfur. And that is going to eat off that chlorine and give you something that looks like this. Now you have a plus charge on your oxygen. Got that R group sticking out. And remember, you took off that chlorine earlier, so now what he's gonna do is he's gonna come in, take that hydrogen away. That gets rid of the plus charge. And so you're gonna be left with this. Remember again that this R group is just gonna be this whole thing. And also, you're gonna see this abbreviated a lot of the time as, wait, I'll do this in a different color. This is not a triple bond, this is just equals. You're gonna see this abbreviated, like Sydney says, as OTS. Because if you look at the oxygen, remember this is the oxygen that came from the alcohol at the beginning. He's just over here, you added TS. Does that make sense to everyone? You're gonna do something really similar with mesyl chloride. I'm gonna go ahead and write out that methyl group instead of writing R because it's not too bad. Okay, what's the first step? Anyone remember? The lone pairs are gonna attack what?
Sulfur.
Yeah, someone said it, thank you. They're gonna attack the sulfur, take off the chlorine. You're gonna end up with this guy, again with the plus charge. Only real difference here is instead of that whole nasty looking, ooh, that's not a nice double bond. Instead of that gross R group with all the benzene rings and such, you're just gonna have that methyl. Again, you're gonna have chlorine come, take off that hydrogen, get rid of that plus charge. Oops, I forgot my oxygen, don't do that. There we go. And that will look like, you might see it abbreviated as the following. Generally, professors will just let you abbreviate it. They might show you this at the beginning just so you know what they're talking about. But again, same oxygen here, same oxygen here, same oxygen here. And again, the whole point of doing tosylation or mesylation is to take this alcohol, which is a bad leaving group, and make it into a good leaving group, either this or this. Does that make sense to everyone? Okay, so now we're going to talk about some characteristics. So the formation step does not change the stereochemistry of whatever compound you're working with. So let's say, for example, I had this alcohol again because we want to get rid of it. Do you guys want to tosylate or mesylate? It doesn't matter. Someone just shout one out.
Mesylate.
Sounds good. So we're going to mesylate it. Remember MSCl, you could, I suppose, draw out the whole structure if you wanted. It is good to know because sometimes they will show you the structure. If you don't remember, you might be like, what the heck is this? I'm not going to show you the mechanism because you've guys seen it, but you're going to end up with this guy. So you're going to see that your alcohol starts on a wedge. This OMS ends on a wedge. So this first step has not changed the stereochemistry. Does that make sense to everyone? So the only point where stereochemistry is going to change is if, for example, you were to do an SN2 reaction. So if we were to take this guy, let's do NaCN, and I'm just going to go ahead and focus on the SN2 reaction for now, because that's how I show you the stereochemistry. Once you do that out, you're going to end up with something like this. So you want to note that your OMS started on a wedge, ended on a dash. Does that make sense? So there was inversion of stereochemistry. All right, inversion. Does anyone have any questions on that before I move on? All right, so now we're just going to be doing 3 practice. I think this presentation is going to be on the shorter side, so we don't have much longer, don't worry. We're going to do this compound. We're going to put tosyl chloride on it. So remember, tosyl chloride is going to be that really funky looking one. That was a really awful hexagon. It's going to look something like this, I believe. And so when we add this on, you could either draw it all out if you wanted to. So something like, oh my gosh, it's going to be ugly. So something like that, or you could simply just do this. And so now we're actually going to take that compound we just made and then do another reaction to it. Remember, because again, generally when you're going to tosylate or mesylate something, that's only so you can do something else to it by making that alcohol a good leaving group. So we have OTS. So we have NaCN. That's going to be, if you remember, pretty great nucleophile. And then you also have DMF, which is polar aprotic. So based on these two things, what kind of reaction do you think is happening?
SN2.
Yeah, perfect. So it's probably going to be an SN2. Remember, when you're doing an SN2, you want to check your substrate. You want to make sure it's either methyl, primary, or secondary. So let's look at them. So here's where the OTS is, and that's going to be secondary. So we are all good there. No problems. And we're going to go ahead and put that NaCN. And this is going to look like the problem we just did on the other slide, where you get inversion of stereochemistry. Anyone have any questions? Okay. Next problem, same thing. You're going to see that a lot of this is pretty similar, and it's not too bad as long as you don't have to like draw out the entire mesyl or chloral, or not mesyl, mesyl or tosyl group. So I'm just going to go ahead, take this. Remember, stereochemistry does not get inverted. So you end up with the same thing. All you did was take off this OH, put this OMS. And take this down. And so we have NaOET. We also have heat. And if you remember, heat is going to mean we prefer one of the elimination reactions. So based on this, the NaOET, do we think it's E1 or E2? So it's going to be E2 because this is generally a pretty good nucleophile, also pretty good base. Remember, I'm just going to draw the E2 product because we have this heat there, which means we favor E2 as opposed to SN2. And so I'm going to go ahead and draw part of this. And I'm going to go back over here and let me label these. I'm going to make this carbon 1 and carbon 2. So the double bond's either going to form on the left side of OMS or the right side of OMS, right? So which side do you think it's going to go on? Do you think it's going to go connect to carbon 1 or carbon 2?
Carbon 2.
Close. So this one's a little bit tricky. You want to remember that when you're doing your elimination, you want an anti-periplanar hydrogen. So reimagine drawing in our hydrogens. This is a good time to draw them. You're going to see that this is on a wedge. This is on a wedge. So that's a no-go. You can use this hydrogen, though, that's on a dash. Does that make sense? So your double bond is probably going to go here. Does anyone have questions?
For tosylation and methylation, does it always, mesylation, does it always occur in 2 reactions instead of 1?
So no, mesylation and tosylation, they're just going to occur by this mechanism, which is just, you can imagine it as one reaction. The only reason why I did the second reaction is to show you an instance of tosylation or mesylation being applied, because usually like when we do tosylation or mesylation, it's so we can get a certain product, because remember, this alcohol is going to be a bad leaving group. So if we take off this alcohol and put a tosylate or a mesylate on it, that's usually because we're trying to get to some other product. Does that make sense?
Yeah, thank you.
And so our final practice, we are almost there. Just gonna be this guy again. Remember, just draw out, oh, that is a bad benzene. That ring.
I have a question.
Yeah.
So do we always do this when when we see like a alcohol? Are we trying to like get rid of an alcohol or like make it a good leaving group?
Generally, like you'll see when you have synthesis problems in 3570 and 3580, they'll give you a lot of ways to make alcohol and other bad leaving groups into good leaving groups. So if you remember what Sydney was saying earlier, she showed you some other ways to also make OH into a good leaving group. Mesylation and tosylation is just one of your options. Sometimes when you have a synthesis problem, the professors will provide you with certain reagents or compounds. So like, for example, they might provide you with tosylate or mesylate, but not with some of the ones Sydney provided. So it's always good to know all the different ways you can turn a bad leaving group into a good leaving group and that kind of thing. Does that make sense?
Yeah, makes sense.
Perfect. So we're gonna go ahead, do the same thing we've been doing, just bring them down here. I'm just gonna put them on the other side, but this is still a dash. I just drew them here because it's kind of awkward to put them here, but it doesn't matter. And remember, CH3OH is going to be polar protic, because I said aprotic last time, and then Sydney corrected me. Don't listen to my 8 a.m. brain. This is the proton. And so knowing this, we also know it's not a great base or anything. So given this, what kind of reaction do we think is going to happen? I'll get rid of that. It's probably not going to be SN2 or E2. Those are out. So we're left with SN1 and maybe E1. And so we're going to get the SN1 product. Going to be this guy. Plus is enantiomer. If you want me to draw that out, let me know. And also the E2 product. So I'm going to put SN2, not SN2, sorry. SN1, there we go. And then maybe the E1 product. If, for example, we added heat, then E1 would definitely be a major product. So let me fit this in. There we go. Do you guys have questions on that? Do you guys have questions in general? Because that is the end of the lecture today. It's kind of a short one.
So it could be both SN1 and E1?
I believe, yes. Because CH3OH is not going to be a great nucleophile. Kind of like a mediocre nucleophile. I'm just going to say nucleophile. But it is polar aprotic, or not polar, oh my god, I said it again, polar protic. So if we, for example, were to add heat, then we imagine that E2 could, not E2, E1 could probably happen.
Can you draw the enantiomer, please?
Yeah. So it should be the same guy, just with these two flipped. So now the OCH3 is on that wedge instead of that dash.
Thank you.
All right, I'm gonna hang out for a couple more minutes if you have any questions. If not, you're totally free to leave. But yeah, I believe Sydney's still here as well if you want to ask her questions.